Hello, this is Philip Myers of PEMY Consulting. Welcome to Strength of Materials for Plant Engineers. This is part 5, continuing stress transformations. What we are really interested in when dealing with the strength of materials is the state of the stress at a point. But we retain the concept of a stress element because a stress, even at a point, depends on direction. In other words, on the orientation of the stress element. So in stress element A, we have tensile stresses aligned with the axis of the bar, but no shearing stresses and no normal stresses on the orthogonal planes of the stress element. But rotate the stress element to B, and we now have shearing stresses and normal stresses on all faces of the element. Before we get into the math of the stress transformation equations, let's remind ourselves what we're doing. The stress square is here, and the normal is pointing in the x direction. We're going to rotate through angle theta so that we can obtain stresses, the state of stress in the rotated x prime, y prime coordinate system. This is what we're after in the new x prime, y prime coordinate system. This isn't as bad as it looks, so let me explain. If we take a slice from the stress element shown here, we can determine the transformation equations needed to convert known stresses for the stress element at one angle to any other angle theta. So in this case, this is theta. Recall that the equilibrium equations of statics apply to forces but not to stresses. So we use the areas of the faces of the element to get the areas. In this case, we have this face will assign delta A, and these areas then would be delta A cosine theta, and this would be delta A sine theta. Cosine theta would be the length of this face relative to the hypotenuse, and similarly for sine theta. Then if you multiply this by sigma x, the normal stress in the x direction, we have the force shown here by this arrow. We do the same thing for the shear stresses and the normal stresses on the other faces. In order to go through all of these equations, and I'll do it just once for the top equation, we want to get organized. So anything in the horizontal direction scales by cosine of theta, as we've already seen. Anything in the vertical direction scales by the sine of theta. Another thing we can do to get organized is to jot down the various arrows that are shown on the original face of the stress element by the 4 bubbles. So if we sum the forces in the x prime direction, we have that we'll start with sigma x prime delta A here. If you'll notice, all the other forces are opposing it. So for example, for item 1 we have tau xy delta A sine theta, which is in the horizontal direction. That's this arrow. We have to multiply it by the cosine of theta because we're rotating to the new angle, and like I said, we're scaling by cosine of theta. The other horizontal force we'll scale is this one here, and you can see that that's 3. It's scaled by cosine of theta. We do the same thing for the vertically oriented forces, and we take tau xy delta A cosine theta, which was a shear force acting on this arrow, this face, and we have to multiply that by sine of theta, and we do the same thing for the 4th component. From statics, the sum of all the forces has to equal 0. So we're going to simplify this on the next slide, but this is how it's derived. Similar things can be done to determine the shear forces, which I won't do. This is a good exercise for you to undertake and to get those equations. So this is a mess, but it simplifies, as we'll see. In the last slide, we derived the equation for sigma x prime. That is the normal stress in the new coordinate system x prime, y prime. We'll now show how that's done. Recall from the last slide that we had sigma x prime is equal to sigma x cosine squared theta plus sigma y sine squared theta plus tau xy times 2 sine theta cosine theta. You can see that from these trigonometric identities we can substitute. For cosine squared theta, we can substitute this expression in here. For sine squared theta, we can do the same thing. And finally, for 2 sine theta cosine theta, we can substitute sine of 2 theta. If we do that, we can pull out the sigma x and sigma y over 2 right here. And because both terms have cosine 2 theta, we can pull that out and take the sigma x minus sigma y over 2, part of it, and multiply it, and then this stays the same. A good exercise for you is to repeat these exercises for sigma y prime and tau x prime y prime. When you do sigma y prime, you have to rotate the plane and take the slice pi over 4 further, which is in the counterclockwise direction. Notice that if we add the normal stresses, sigma x prime plus sigma y prime, these terms drop out. They cancel each other. And so what we have is that sigma x prime plus sigma y prime is equal to sigma x plus sigma y. This says that no matter what the stress orientation is, the stress plane or the stress element, the sum of the normal forces acting in orthogonal directions is always the same. Another way of saying it is that the sum of the plane normal stresses is invariant to coordinate transformation. So in summary, we've learned that a stress element represents the stresses at a point. The stress state depends on the direction of consideration, and that's why we have to retain the idea of a stress element. The math is a little bit tedious, so you might wonder why bother and why we do. You have to have seen these ideas at least once, and then you don't need to use them much anymore. You can rely on what we're trying to get to, which is the Mohr circle. It's a graphical way to simply conceptualize and understand the ideas that we've been going through on transformation of stresses to different angles. 3D transformations are more complex, so we're not going to cover those here. And next time we'll go through an angle where we look at all possible angles so that we can get some insight into how the stress transformation really works. Thank you, and we'll see you next time.